Federal Drive is presented by GEHA, Government Employees Health Association, proudly providing health and dental benefits to federal employees and their families. Visit GEHA.com.
NASA's successful demonstration of laser communications during the Artemis Two mission marked a turning point for a technology that has been in development for years. It proved that optical communications can support human spaceflight operations, sending high-resolution imagery and scientific data as 4 astronauts traveled around the moon. Nikki Desch is the project manager for the Orion Artemis Two optical communication payload system at NASA's Goddard Space Flight Center. She talked about the capabilities with Federal News Network's Anastasia Obis.
Throughout the mission, it was responsible for downloading up to 484 gigabytes of data, including high-res imagery, high-definition videos, mass amounts of science data, as well as engineering data that was used by scientists and engineers throughout the mission, and was also shared with the world in the form of pictures and videos and live streams.
Yeah, amazing. And you described it a little bit, but for those who are not familiar, talk a little bit about the system, its benefits, kind of the limitations it's been trying to overcome, how long NASA has been working on it, and why it's so important to the Artemis mission.
The O2O system has been in development since 2017. It was part of a larger effort to advance the technology readiness of optical communication payloads for various types of space applications, including from LEO from low Earth orbiting satellites, geostationary satellites, as well as lunar applications. The importance of O2O in optical communications is that it provides a high data rate capability. As our science instruments continue to advance in their ability to collect data, they become more sensitive. Then that means that they're collecting significantly more data throughout their mission lifetime, and that is also true for human spaceflight. Because of that, there is a need to actually download significantly more data today than there ever was before. What optical communications does is it provides a way to download these extremely high, large volumes of data using a payload that takes up significantly less space, and it weighs less and uses less power than traditional radio frequency systems. That being said, though, it does have some challenges. The traditional radio frequency systems, while they are not able to transmit nearly as much data as optical communications in the same amount of time frame, radio frequency systems can be available 24/7, and they're not limited by atmospheric effects as optical communications is. Because optical communications uses infrared technology and infrared lasers to transmit these high data rates, the signals do often get impacted by clouds and other types of atmospheric weather effects. However, that is easily mitigated by having a very diverse ground segment and by having multiple stations, so that the optical communications terminal in space can point to an available ground station should the one that they're communicating with become unavailable.
Let's talk about those ground stations.
Sure.
And you've been working on the development of ground systems. So first, talk to us about the components of the ground system.
An optical ground segment needs to have multiple ground stations, and generally they are geographically diverse. For O2O, we had a ground station at the White Sands Complex in New Mexico, one at the Table Mountain facility in Wrightwood, California, as well as one at the Australian National University in Canberra, Australia. Each of these ground stations has a slightly different design. They have different types of telescopes, but ultimately they're all able to receive the same signal from Orion. And so they're back. So all of their modems are this is probably way too detailed, but CCSDS, high photon efficiency compatible. And so when the data is actually received by the ground station, it gets processed and then is transmitted via our terrestrial networks over to the Johnson Space Center Mission Control Center.
There are a total of 2 ground stations.
So there were two that were baseline for the mission.
Right.
Those were the Table Mountain facility and the White Sands complex. However, we partnered with Australian National University to include them as an experimental station, since this is something that they were building up independently from, as part of a collaboration with NASA, but something that they were building up on their own, and we wanted to include them in this partnership and in this demonstration.
Oh, that's cool. How did that go?
It went excellent. They worked the first time. They supported data rates up to 260 megabits per second, which was the maximum for the for O2O, and their ground station performed excellent.
Amazing. Are there plans to build out more ground stations in the future?
So there is definitely a need to have more optical ground infrastructure, but it doesn't necessarily have to be NASA's ground infrastructure. It could be partners with other space agencies, as well as commercial providers. I'm aware of a number of companies that are exploring or have built up optical ground capabilities that support low Earth orbiting satellites, and their optical communication signals, payloads.
Could you maybe expand on some of the challenges that you had to overcome when building those ground systems?
One of the biggest challenges is the pointing. It requires very precise pointing to a very small, refined spot in the sky. When the space terminal is actually able to point on the ground, when they're at lunar distances, that beam is the size of about 6 kilometers in diameter. It's very, very narrow. So being able to have the ground station precisely point and transmit a beacon up to the space terminal, to then have the space terminal then precisely point back, see and acknowledge that the ground station beacon and precisely point back to the ground terminal is extremely difficult. It's extremely difficult, and it's especially difficult for lunar distances. It's much more challenging than it would be for LEO or even geo type missions. So that's one of the biggest challenges.
That's Nikki Desch, project manager for the Artemis Two optical communication payload system at NASA's Goddard Space Flight Center. Watch her full conversation with Anastasia Obis at federalnewsnetwork.com.